This is the second part of the supplementary video for Lecture 4. In this video, we will go over the two theoretically important exercises together with the justification of calculation of limits. Now let's look at the first problem. So let p of x be a polynomial function. Then we want to prove that for every number a, limit of p of x is the same as p of a. Okay, so let's start by recalling what is a polynomial function. So we say p of x to be a polynomial function if p of x can be written as b sub n times x to the n plus b sub n minus 1 times x to the n minus 1's power plus all the way down to the power of x becoming 1, namely b1 sub b1 times x plus b sub 0, which is the constant term. So here, n is a natural number, so which means n can take 0, and b sub n all the way down to b sub 0, those are real constant numbers. So if p of x can be written in such a way, then we would say p of x is a polynomial function. Okay, so now we are looking for the limit. This means we are looking for the limit of this whole thing over here. So what can we do with this guy? So first notice that this is a finite sum of constant multiples of monomials. So because this is a finite sum, so I can repeatedly use the sum rule to break this guy up into the summation of every single term over here. So for example, if I am using applying the sum rule towards the sum of these underlying terms, then the sum rule will tell me that this is going to give me the limit of the first guy plus the limit of b sub 0. Okay, so then the last term in the first guy will be b1 sub x. So then if I use the sum rule again, applied to these two guys, then I will be able to kick this guy out so as to get limit of everything except the last two guys plus the limit of b1x plus the limit of b0. So this is actually what I can do. So I can repeat this whole process until I kick out every single thing after b sub nx to the n. So at the end of the day, what I will obtain is the limit of first guy plus the limit of the second guy plus the limit of each individual guys over here. So that will be the sum of limits like this. All right, so this is done by repeatedly using the sum rule of limits. Okay, so then for the next step, I will use the constant multiple rule to kick out these coefficients b sub n minus 1, all the way up to bn and b0. So that way I will obtain b sub n times the limit of x to the n plus b sub n minus 1 times limit of x to the n minus 1 plus all the way down to b sub 1 times limit of x, and finally plus b sub 0. Well, what remains is going to be a limit of 1. Okay, so then finally, I can use the power rule to handle each individual limit. So remember, so the power rule tells me that if x is approaching a, then x to the nth power will approach a to the nth power. So that way we know that the first guy is simply going to be a to the n, this guy is simply going to be a to the n minus 1, and all the way down to, so this is a to the 0, so namely equals to 1 as well. So you could either use the power rule or use the constant, the limit of constant functions. All right, so at the end of the day, we will be able to get b sub n times a to the nth power plus b sub n minus 1 times a to the n minus 1th power, and so this will be adding all the way down to b sub 1 times a, and then plus b sub 0. Okay, but what is this guy? This guy is nothing but p of a. So that way we manage to prove that limit of p of x is precisely p of a. And that concludes our proof over here. So this will be the solution to the first theoretically important exercise. Now let's look at the second exercise. So let r of x be a rational function. Then for every number a in the domain of the function, we also have the limit of r of x as x approaches a equals to r of a. Okay, so we need to recall what does it mean for something to be the rational function. So recall that we say R of x is a rational function if R of x is a quotient of two polynomial functions P of x and Q of x. So this is a definition for a rational function. And if we want to evaluate the limit of R of x, this is the same as asking the limit of the P of x over Q of x. Okay, now it's important for us to specify that the number a is inside the domain. So indeed, let's actually pick the number a to be in the domain of the rational function. And the important thing for this restriction is that Q of a, so namely the denominator evaluated at this number, will give me a non-zero number. So Q of a is non-zero. Okay, so now to evaluate the limit of R of x is basically the same as evaluating the limit of P of x divided by Q of x. Okay, so we can distribute this limit into the numerator and the denominator and rewrite the whole thing in this way. And this is because we could use the quotient rule. So notice that to use the quotient rule, we need to guarantee that the limit of the denominator is non-zero. And this will be seen in the next step. And well, in the next step, we will simply say that the limit of P of x equals to P of a, and the limit of Q of x equals to Q of a. So this follows from the conclusion of the previous exercise because P of x and Q of x are polynomial functions, and we know that the limit of a polynomial function is the same as the function value of the polynomial function at the point A. So that's how we can conclude the limit of P of x equals to P of a and limit of Q of x equals to Q of a. And in particular, since we have Q of a is non-zero, so this computation makes sense. And then yeah, we can use the quotient rule to conclude this. Okay, but what is P of a over Q of a? P of a over Q of a is precisely the function value of the rational function at the point A. So this way we manage to prove that the limit of R of x equals to R of a, and that will be the full proof. Now let's work on number 6. We need to evaluate this limit, and also we need to provide justification for each step by indicating the appropriate limit laws. I don't think this will be a fair problem for the test because, well, to justify each step requires a lot of writing, but in the test, we have got very limited time, so that's why this problem is highly unlikely to appear in the 1-hour test you will have to do during the semester. But for a final exam, this is completely appropriate. So that's why I still need to mention this. So there are two ways of writing the full argument. And let me first use the textbook method. Okay, so to evaluate this limit, and then we need to first handle the square root outside. And well, we could switch the order of taking the square root and limit and place the limit inside the square root. And for this, we need to use the power law. So just briefly recall what the power law says. Well, the power law simply says the limit of any power of f of x. So this is going to be the same as the power of the limit as x approaches a. So for this case over here, we are just regarding this square root as taking 1/2 power, and then we invoke the power rule, power law used with the power 1/2 over here. So that way we will be able to place the limit inside. So this follows from the power law. Okay, so then for the next step, I will just distribute the limit into each individual term. So that will be limit of u to the 4th power plus limit of 3 times u plus limit of 6. Okay, so this is by the sum law. So the limit of f of x plus g of x equals to equals to the limit of f of x plus limit of g of x. As x approaches a. Okay, so then for the next step, let me just leave everything over here, but just pull out the constant 3. So for the next step, I will just leave the first term unchanged. And then I will pull out the constant 3 in the front of the corresponding limit. And then I will just leave the 6 over here unchanged. So this is by the constant multiple rule. So this basically says limit of c times f of x, where c is a constant. So this is simply going to be the constant times the limit. All right, so this is just the justification why we can actually move the 3 outside. And now we could use the power law and the limit of constant functions to evaluate. So the first guy will be minus 2 to the 4th power, and the second guy will be 3 times minus 2, and the last guy will be 6. So this is by power law. So I won't repeat the details. And then plus limit of a constant. Okay, so this is the justification of this computation. And finally, we can just perform the computation. So minus 2 to the 4th power, it will be 16. And then 3 times minus 2, that will be minus 6. And finally, it will be plus 6. So 16 minus 6 plus 6, the answer will be root of 16. And root of 16 is going to be equals to 4. All right, so this is the textbook method of writing the justification. Okay, so let me just briefly mention what's going on. So in an exam, you will not be asked to write down the details what each law actually means. So which means over here, so this part of the steps over here, when you are trying to write in an exam, so this part you do not need to write it. So let me actually mark them in green. So yeah, all you need to say is actually by power law, then you have this, and by sum law, you have got this, and then by constant multiple law, I would better say it's actually law, because rule is probably the term that the word preserves for derivatives. For limits, we use law. Okay, so then, yeah, but then you certainly need to say power law over here and the limit of constant over here. So yeah, this is how you can write in the exam. So you can simply forget about this part. Okay, so as you could see in the previous process over here, so writing this limits repeatedly is really annoying. So that's why I will just do it in another way that is also acceptable in the test. So this way of writing is kind of reverse to the previous writing. So let's actually start by saying as u approaches minus 2. So then we know that u to the 4th is approaching minus 2 to the 4th power, which is going to be equals to 16. So this is by power law. So, and then 3 times u is approaching 3 times minus 2, and the answer will be minus 6. And this is by constant multiple rule. Law, actually, yeah. Okay, so, and finally, the constant 6 will approach 6, and this is by limit of a constant. Okay, so then, start from these 3 guys over here, I can conclude using this sum law. We can say that u to the 4th plus 3u plus 6. So this will approach 16 minus 6 plus 6, which is going to be equals to 16. And this is by the sum law. Okay, so what do we have from after that? Then after that, we could actually use the power law. So the root of u to the 4th plus 3u plus 6. So this is going to be equals to u to the 4th plus 3u plus 6 to the 1/2 power. And then from the power law, again, we conclude that this guy is approaching 16 to the 1/2 power, which is going to be root of 16, which is equals to 4. And this is by power law. All right, so what do we have? We see that as u approaches minus 2, the root of u to the 4th plus 3u plus 6 is approaching 4. Therefore, we conclude that limit of root of u to the 4th plus 3u plus 6 as u approaches -2. So this is actually going to be equals to 4. All right, so you see that this is the computation and this is the justification over here. And I think this is much more convenient to write. Okay, so this concludes the second part of the supplementary video. So please definitely let me know which way do you prefer. So do you want to see me writing on site? Or do you want to see that it's actually like a slideshow as I did for the two theoretically important problems? So please definitely let me know your preference. Okay.